Over the past couple millions of years, there have been pretty stark fluctuations in global climate. For example, about 20,000 years ago, Montreal was covered in about 3 kilometers of ice. It obviously isn't now, and it hasn't been for the past few thousand years, but it also wasn't 120,000 years ago or at any of the peaks you see in this graph that shows the last 800,000 years before present. That's what KBP means, in both delta deuterium, which is a temperature proxy given from the ice core epicodome C, and CO2 in parts per million from a stack of Antarctic ice cores. You can see that temperature and carbon dioxide fluctuate in tandem, and that there are these quasi-periodic glacial cycles. This graph actually doesn't show modern anthropogenic warming. If it had that data from the past century, you would see carbon dioxide going up above 400 parts per million. But in contrast to today, where we know what's causing climate change, it's anthropogenic carbon emissions, that definitely wasn't the cause of the ice ages, what caused them to wax and wane. If you're looking at this data from 800,000 years ago, our species wasn't even around, and the numbers were way smaller, and no one was industrialized. So, what causes these ice ages is one of these large questions in paleoclimate. There's been spectral analysis done on a variety of paleoclimate records over the past 50 years, and it supported the work of this early 20th century Serbian mathematician called Milankovitch, who proposed that astronomical changes actually cause these ice ages. So Milankovitch's theory was that there are these small cyclic changes in Earth's orbit on timescales of 20 to 100,000 years, or I guess there are some supercycles going to 400,000 years, that influence the amount of radiation the Earth receives. Now, incidentally, the changes to the entire Earth's radiative budget of incoming solar radiation or insolation, ice age timescales, is pretty small and probably could not cause the kind of climate response that we see. However, if we look more regionally, it looks like summer insolation around the northern hemisphere high latitudes, maybe 60, 65 degrees north, has a pretty strong effect. It lines up fairly well with the forcing and responses that we see. This is no accident. We have a lot of land in the northern hemisphere at those latitudes. We don't in the southern hemisphere. So essentially, there are places that we could grow glaciers in the northern hemisphere, and that glaciers did grow and recede over ice age cycles. In the southern hemisphere, Antarctica has remained glaciated for several millions of years, with possibly some exceptions. And a lot of the rest of the southern hemisphere is water, or it's tropical land. In contrast, we've got very large continents in the northern hemisphere mid-latitudes, and there have been huge glaciers that have grown and receded, like the Laurentide and Eurasian and Fennoscandian ice sheets. And so we think that summertime insolation can cause melting to occur if it is large enough. So then if summers are warmer, the glaciers recede. These parameters of astronomical forcing are as follows. Eccentricity is on about 100,000 year timescales. Obliquity, or the Earth's tilt, is on about 40,000 year timescales. And precession, which we'll get into, is on about 20,000 year timescales. So eccentricity refers to how elliptical the Earth's orbit is. This varies from almost nothing. It's a unitless parameter, but on our planet, this varies from about nothing to about 0.06. So in a time of low eccentricity, the Earth's orbit is more perfectly circular, whereas in a time of high eccentricity, it's much more elliptical. Eccentricity is the only orbital parameter that actually changes total annual insolation all over the planet. And it's comprised of several different components. A lot of them are around 100,000 kiloyears, sorry, 100,000 years. One of them is more like 413,000 years. So this shows up in our paleoclimate records as being around 100,000 and around 400,000 years. We see peaks in spectral density. Now, perihelion is the time when we are closest to the sun, and aphelion is the time when we're farthest away from the sun. This can actually be a little counterintuitive if you are, as you statistically probably are, watching this from the northern hemisphere. So actually, when we are closest to the sun, that's early January. The northern hemisphere is in winter because it's tilted away from the sun. Whereas when we are farthest from the sun in early July, the northern hemisphere is actually in summertime. If Earth didn't have a moon, if there had never been that Mars-sized object that crashed into the Earth and caused the moon to form, then we would be perfectly up and down. Poles would never really get any light, and obliquity would have no effect on global climate. However, we have this 20-some degree axial tilt. So currently it's 23.4 degrees, but it actually varies between 22.1 and 24.5 degrees on this like 41,000 year time scale. This impacts the pole to equator temperature gradient because if obliquity is lower, then the Earth is more perfectly upright, poles are colder, the equator is very marginally warmer. But if obliquity is higher, then the poles get more insulation. So in times of high obliquity, you're more likely to see those high latitude glaciers melt. Incidentally, this, unlike what we're going to talk about next, has the same effect on both hemispheres. It's just a pole to equator difference that you're seeing because of obliquity. Precession is probably the most complicated of all of the orbital parameters that we're talking about. It's sometimes referred to as wobble. Precession refers to this change in the actual direction of the Earth's axis. This pertains to seasonality of perihelion and aphelion. So today we have aphelion in early July and perihelion in early January, but 10,000 years ago in the early Holocene, it would have been the reverse of that. If you are into the zodiac, it's one way of thinking about this. 10,000 years ago, all of the zodiacs would have been in the opposite position. So where the stars are in March now, they would have been there in September at that time. The climate effects of precession are opposite in each hemisphere. So today, because the southern hemisphere experiences summertime at perihelion, they experience marginally stronger summertime warmth, a very marked, and seasonality in the northern hemisphere is slightly milder because we're closest to the sun in our winter and farthest from the sun in our summer. Now, in practice, seasonality in the southern hemisphere probably on average is less than seasonality in the northern hemisphere just because most of the southern hemisphere is water and more of the northern hemisphere is land. But these effects would be more extreme if we were looking at the early Holocene's configuration. Because the climate effects of precession have to do with perihelion and aphelion, they are modulated by eccentricity. At times of very low eccentricity, precession has very little climate effect. There are several different components to precession, but the main ones are about 19 and 23,000 years. And so these are what we tend to see in climate records. Most of them look like about 20,000 years. We see these precessional peaks in some records. So we think that these orbital parameters are important because we see them show up in our climate records. Here I have a stack of benthic isotopes. So these are oxygen isotopes found in calcitic microorganisms in the deep sea. And this particular picture shows the record going back about 3.5 million years. Um, the scale is in kiloyears, so it looks like 300 or 3,500 years. This is affected by global ice volume and also to some extent by temperature. Weirdly, we see different orbital parameters taking precedence at different times. So from about 5 to 3 million years ago, basically in the Pliocene, we see this strong periodicity of 20,000 years. Actually, it's not as strong as what we see later. From about 3 to 1 million years before present, we see a much stronger periodicity of about 40,000 years. So that means that before about 3 million years ago, what we mostly saw was precession, and after that, what we mostly saw was obliquity. And then, if we look at the last million years, we see a stronger periodicity at about 100,000 years. Now, this is actually contested. It's possible that what we're looking at is a combination of precession and obliquity rather than strictly seeing eccentricity over the last million years. But at any rate, it seems like the cycles have gotten longer over time, and they've also gotten stronger in amplitude over time. You see much more variation in the last 800,000 years than you see in like the record 2-3 million years ago. The reasons for these changes are contested, but essentially we think that as global ice sheets have grown overall, as there's been general climatic cooling over the past 5 million years, the Earth has been sensitive to different types of forcing. There's still a lot of room to be done in terms of research on this subject, though. It's a very exciting area of research.